Hello everyone and welcome back to this next lecture. So this is where we had left off in the previous lecture where we had compiled the driver lib project. So now with both projects compiled, we are now ready to execute this program, execute these projects. So with this, I'll bring the microcontroller into the video. So you will now see the microcontroller in the video. Now in this case, since we have a three-phase converter, we have now 6 connections for each CPU from the EPWM pins to the solderless breadboard. So we have connected pins A and B of EPWM 1, 2 and 3 to the solderless breadboard, as well as EPWMs 4, 5 and 6 to the solderless breadboard. So this is where we're going to make our connections. So currently the oscilloscope probes are at S1 and S2 of CPU1, which corresponds to pins 1A, pins EPWM 1A and EPWM 1B. Of course, we'll be moving it as we continue observing the oscilloscope waveforms. So with this, I'm going to zoom in to the oscilloscope. So this is now the oscilloscope zoomed in. So now we will enter the debug mode. So it has been loaded onto the processor and now we can select it and click on continue. So we get the usual waveform that we see. So now in this case, we are measuring the two devices in the same phase, that is phase A. And that is why we are getting complementary gating signals. So now in this case, I'm going to move the blue waveform from S2, that is the lower device of the phase A, to the upper device of phase B. Right? So this is now a comparison between two phases. And as you can see, both of these gating signals seem to be sinusoidal templates. That is the width of the pulses is changing from the maximum to the minimum. But you will see that they are both displaced by a certain phase. So this indicates that what we are producing at the output of the converter is indeed a three-phase output voltage. And just for the sake of completion, I'm going to now connect the blue waveform to phase C, that is the gate signal of the upper device of phase C. And here too you see there is a phase angle difference. This is between phase A and phase C. And one last check, I'm going to now connect the yellow waveform to upper device of phase B. And once again you will see there is a phase angle difference. Right? Now in this particular case, to verify whether the exact pulse widths are as expected, I would recommend that you use the same process that I did before. That is, you comment out the phase angle, the statement where the phase angle is being integrated, and instead you put the phase angle in the watch window and manually place values for the phase angle starting from 0 degrees all the way up to minus 180 degrees or 0 or 180 degrees, and then verify for yourself that for each and every value of the phase angle, different values like from 30 degrees, 60 degrees, so on and so forth, you are getting pulse widths in all three phases as expected. So this I will leave to you as an exercise. So with this, we are now ready to connect CPU 2. So I'm going to go ahead, click on it, connect the target, and then I will load the program. So go into driver lib, go into CPU2 RAM and click on dot out. So we have the red dot, which means it has been programmed. So now I'm going to click on the run. So let me change over my oscilloscope connections. First, I'm going to connect it to the two devices of phase A as usual, because that is my usual starting point. And we get the usual sinusoidal templates, but this time we have complementary gating pulses. And that is only expected because these are the two devices in a single leg. So now I'm going to change the blue channel output to phase B. That is, I'm going to connect it to the upper device of phase B. And you see the same phase angle difference between them, which indicates that we are indeed comparing two phase difference, or at least two modulation signals that are differing by a phase angle with the same triangular waveform. And finally, I will connect blue output to phase C. And this too, you can see, has a phase angle difference. And one last connection, and that is yellow phase goes to phase B. So we are now comparing B phase and C phase. And once again, you see the same phase angle difference. So in all these cases, we are seeing that we are now able to generate gating pulses for a three-phase converter, providing a balanced set of modulation signals for comparison with the triangular waveforms. So at this, I'm going to end the microcontroller video, and we are also at the end of this lecture. So this is actually a very simple implementation because there is not much to do in terms of actual implementation. We just have to generate the modulation signals, and the rest of it is done by the PWM module itself. If any of this did not work, or you faced any other issues, please post in the Q&A forum and I'll be happy to help you. Otherwise, I will see you in the next lecture where we will get started with the space vector modulation approach for providing gate pulses to a three-phase converter. Thank you so much for listening and see you soon. Goodbye for now.